Owen Mason, and this is my Physics 2211 Lab 4 about oscillating springs. Introduction. In this lab, we are analyzing the motion and energy of an oscillating spring that is moving in x and y dimensions. We then compare the energy and position graphs to a predicted model of an oscillating spring that we developed through glow script. We'll analyze a few concepts. The main one is Newton's second law of motion and his momentum principle. When analyzing the spring, we have to consider the forces that are acting on it. The forces acting on it are the force due to gravity, which is mass times gravity, and the force acting on the force of the spring acting on it. And we also have to consider the energies of the spring as it oscillates. Kinetic energy, which is 1/2 mv squared. Spring potential energy, which is 1/2 ks squared. And gravitational potential energy, which is mg times h. These combine to get to total energy. When analyzing the motion of the spring, we need to consider its updating velocity and position. We use the position updating formula and the velocity updating formula we developed through integrating Newton's first law, the momentum. We analyzed the motion of the spring using tracker, and we kept track of it by plotting the center of mass of the spring as it was oscillating back and forth. We were given a few initial conditions of the spring too that we got from the pre-lecture videos, and also we had to calculate a few ourselves. The mass of the spring is 0.402 kilograms, and its initial position is in the x negative 0.03 meters, and in the y it's 0.708 meters negative, and its initial velocity is 0, 0, 0. We also had to calculate its at-rest length of the spring. We use this by setting the force of gravity equal to the spring force when it's at rest, and from there we were able to rearrange the spring equation and calculate that its at rest is the length of the spring is 0.123 meters. Glow script code that will graph our energy curves and also our predicted model. First, we plugged in the constants like the ball's mass, the delta t, and the initial time, and also the force of gravity, which is 9.8, the spring constant, which we were given in the pre-lecture videos, which is 6.83 Newton meters, and the L naught, which we calculated earlier. And we also plugged in the L hat to calculate the ball's initial position minus the spring force. And we also wrote our equations that would give us the initial energy of the ball at its rest position. Calculate our incrementation of the ball's position along with its new energies as the ball travels. We did this by setting our old energies we set equal to new ones, so that would become our new initials, and then we calculated the updating position of the ball using the position updating formulas that we've utilized in many other labs. And then we calculated our new energies and compared them to the old ones to get our change in energies. In our code, we get this for our energy graphs of our oscillating spring that we got through tracker. The red is the gravitational potential energy. The green is the spring's potential energy. The blue is the kinetic energy of the spring as it's oscillating. And the orange is the total energy of the spring. Next, we also got these position graphs. The red is our experimental data that we got through tracker, and the blue is the predicted model that we generated through glow script. First off, our energy principle, that the change in energy equals 0 in this sense, was satisfied because the total energy in the graph, which is the orange line, stays at 0. This means that there is 0 work being done in the system and that the energy is conserved. My oscillation period for the x position is around 1.65 seconds, and the oscillation based on my y positions is around 1.55 seconds. These are slightly different and most likely are affected due to losses in energy that we might experience slightly through the spring oscillating, losses to friction and loss to thermal energy. And this is important because we'd use the period to calculate the spring's constant to the spring force to the spring constant, and by having slightly different ones we could generate different constants based on this.